Variable pitch propellers. Primary controls. The engine throttle, which is the black levers, controls the engine power setting. The RPM control lever, which sets the required engine speed within the pitch range of the propeller. There's blue knobs on the end of it. The red levers are the mixture settings. Variable pitch propellers can change their pitch angle. The RPM control lever. The RPM control lever is connected to a control unit known as the constant speed unit that is mounted on and driven by the engine. The CSU acts as a governor and maintains the selected engine speed. As engine speed increases, propeller RPM increases as the propeller drive shaft turns faster. The increase in propeller RPM is sensed by the CSU, which moves the propeller blade to a coarser angle. This makes the engine work harder to turn it, thus reducing engine RPM. As engine speed decreases, propeller RPM decreases, as the propeller drive shaft turns slower. The decrease in propeller RPM is sensed by the CSU, which moves the propeller blade to a finer angle. This makes it easier for the engine to turn it, thus increasing engine RPM. Variable pitch mechanisms. Single acting constant speed. Oil pressure operates the pitch change cylinder to the fine pitch. Centrifugal force and a spring move the propeller to coarse pitch. In the double acting constant speed mechanism, oil pressure operates the pitch change cylinder both ways. Variable pitch positions. Extra fine, fully fine, ground fine. This is for easy starting. There's reduced drag. Pitch automatically increases to normal fine, i.e. more coarse, to increase airflow for engine cooling. Fine pitch stops automatically engage, which prevent the propeller from moving back to extra fine, and therefore preventing it going too fast. The constant speed range. For normal operations, propeller speed is sensed and governed by the CSU. Feathering stops prevent the propeller moving into a fully coarse position. Feathered. This prevents windmilling, in other words, the propeller being driven by the wind, in the case of a failed engine. Braking. The propeller is moved past the extra fine position so that it produces reverse thrust. Here's a diagram of a windmilling propeller. There's a very large TAS vector, but propeller thrust is actually in the wrong direction. Feathering. Here's a picture of a feathered propeller. It's in line almost with the relative airflow. Feathering is moving the propeller to a fully coarse position. To achieve this, the RPM lever is usually moved through a gate in the quadrant. This raises the governor valve fully, allowing oil to drain out. The blades turn to the fully coarse position under the action of counterweights and a spring. Unfeathering. Unfeathering removes the propeller from the feathered position. A separate source of oil under pressure is required. On light aircraft, this may be via an accumulator, which is charged during flight. To achieve this, the RPM control lever is moved into the constant speed range. An auto feathering button may be pressed, releasing oil from the accumulator to the propeller. The blades begin to unfeather, and as soon as the propeller starts to windmill, the normal oil supply takes over. Shutdown. On shutdown, oil pressure is gradually relieved by leakage through the CSU, which would send the propellers under spring pressure to a feathered state. Propellers, in some cases, need to be prevented from feathering during shutdown, since starting from a feathered state would produce extreme loads on the engine. Propellers need to be prevented from feathering during shutdown, since starting from a feathered state would produce extreme loads on the engine. To stop the springs moving the propeller to the feathered state, The centrifugal latch is fitted to prevent forward movement of the propeller piston.